As you can see, I'm back working on the Z80 project, and I've been making up a rear panel for it. So this is just a piece of aluminium that I've bent to shape and cut a few holes in. So we've got some holes to mount it. We've got a hole for the RS232 port, and you may be wondering why it's got a main socket and switch on it, because of course we don't have a power supply in this. But that's what this video is going to be about. We'll be starting work on the power supply for it. There are two main routes we could go. We could create a linear supply, transformer, rectifier, capacitor, that sort of thing. Or what we're going to do is design and make up a switching power supply for it. So we're going to design a discrete level switch mode power supply. We're going to do it from scratch. And thanks in advance for all the advice I'll get saying I should use a modern switch mode controller IC. Yes, you could do that. You could incorporate most of the electronics we're going to design and or avoid it by just using a simple modern switch mode power supply IC. But then again, we could have bought a modern Z80 computer. So that's not what this project's about. What we're going to do is design a switch mode power supply from scratch. We're going to keep it as discrete as we can, and it will be along the lines of the type of power supply that would have been available or used back when the Z80 was first available. So along the lines of kind of the Aztec type supplies, that sort of thing. So that's what we're going to do now. I'll get this out of the way. I was going to post this as a completely separate series of videos. I might do that as well, but I'm going to incorporate it into this series just to keep the Z80 theme going, and also it should hopefully make it clearer that I'm not trying to design a modern switch mode power supply. I'm trying to design something that would have been familiar to someone designing a Z80 computer back in the day. So I'll get this out of the way and we'll start the design of our power supply. Okay, so I'll show you the design I've got for the supply so far. That's right, it's a blank piece of paper. So I didn't start designing this until right now. I wanted us to go through this together. Now I'm going to be going into quite a lot of detail with this, so if it's not something you're interested in, just don't watch the video, don't sit and watch it and then complain. That's on you. As I've just said, I'm going to go into a fair amount of detail. I will try to avoid too much complex mathematics. I will have to dip into it now and again, but I will try to skip over the main complexities in that, but I will go into some of the basics. And just bear in mind, this is meant to be for fun, so you can experiment, but having said that, if you're designing a switch mode power supply like this, this will be connected direct to the mains at some point, and if you get it wrong, it will literally blow itself to pieces, or you will electrocute yourself. So just be aware of that. I accept no responsibility if you hurt yourself doing this, so just be careful. I advise you use an isolated and current limited supply when you're testing it especially, but just bear in mind there are some very high voltages and some potentially very high currents in a supply like this. Okay, so with that said, we'll get started. If this is not something you've done before, then you'll hopefully find it interesting. If it is something you're familiar with and you've done, then you probably don't want to watch this video in the first place. So as I said, I'll go into this in quite some detail. So the first thing is where to start, and the easiest place to start with a supply like this is at the input. So what we're going to have here, by the way, I apologise if I look a bit cack-handed when I'm doing this, but I'm kind of looking round the camera. I can't really see the paper directly, so it's not going to come out particularly well drawn, so please bear that in mind. So we'll start off and we have our AC mains input. Now in my case, it's always supposed to be a nominal 230 volts. Where I am, it's actually around 250 volts. So that is something you need to take into account, because when you're calculating the operating point of a supply like this, you need to figure out and design it so that it will operate over the full range it's going to encounter. So we have our mains input. So the first thing we'll do is we'll put in place a fuse. one of the issues with a switch mode supply is if the primary driver transistor is switched on or goes short, it will effectively short circuit the mains that's been fed into the system, and obviously without a fuse that could be quite dangerous. Now this supply, and switch mode power supplies in general, do generate a lot of electrical noise. Also, we need to protect it to a certain degree from outside noise on the mains. So we're going to put a filter as the first part of the input. It's mostly to stop us feeding conducted emissions back out onto the mains, but it will also act to protect the supply from external noise as well. We will also need to take steps to minimize the radiated emissions as well, but we'll come on to that later on. Now these circuits tend to design themselves, so as we go along you'll notice it will start to look very familiar if you've worked on these vintage switch mode supplies. And in fact, if you look at a few of the switch mode supplies that were available at the time, the circuits all look very similar, and that's for that very reason. They tend to design themselves as you go along. Now the first thing we're going to do is put in a common mode filter. So you'll see these. We can make one of these ourselves if we want to, just a ferrite core ring and a couple of windings on it. So it's very easy to make this, or we could just buy one. They are readily available. Okay, so once we've got that, we can put some filter capacitors in here as well. So we have effectively an LC filter. These are normally the notorious reefer caps that you get on the old switch mode supplies. We'll put a MOV in here as well, just to protect the supply from any voltage spikes, any lightning strikes or anything nearby. We don't want our supply being destroyed when we could perhaps filter that out. We also want to filter the output of this, and so we now have the input filter. You could replace this of course with one of the built-in filters that you can get in main sockets these days, but as I said, I'm going to design this as discreet as I can, so we will include all this on our supply. We should of course earth this just to make it a bit safer, and that also means we can incorporate some more filtering. So we have, you're familiar with this, you'll have the X-type capacitor across the supply, then you have Y-type capacitors going to ground. So we normally take a capacitor from each of the two rails, each of the two lines, and we can connect those to ground. So that will be our earth lead. And at this point you can decide whether you want to connect this to one of your 0-volt rails or just put another capacitor on here and link it in that way. It's just meant to minimize noise and give any noise that's generated somewhere to go, so it's damped out and doesn't cause any major issues. So we've got our AC coming in and filtered. Next thing, we want to rectify our mains. So we'll use a bridge rectifier, and then we can connect our incoming mains to our rectifier. And then of course what we end up with is rectified DC coming out. Okay, so this will be our V plus, and this will be our 0 volt. This is 0 volt on our raw input supply, it's not the 0 volt of our output. The output of our supply will of course be completely isolated. So once we've done this, the next thing we need to do is determine whether we're going to design it for multi voltage use. So you'll quite often see on the input to this type of power supply there are two smoothing capacitors on the input side of the supply, and it's up to you whether you do that or not. You can either have a single capacitor across here, or you can put two across here if you want to use this for example 110 or 220 volt operation. I will most likely go for a single capacitor here, but just to keep this as clear as possible, I'll show how these are normally arranged in the vintage supplies, because if you've seen one, then it will make more sense when you're relating it to this project. So if I draw this the way you're most likely to see them in the vintage supply layouts, then you'll have a couple of large electrolytic capacitors, and they'll be arranged in series across the DC output of your rectifier. So they'll be arranged like that. And what this does, it allows you to use lower voltage capacitors, but bear in mind it will also reduce the effective capacitance. So if we have, for example, two 100 microfarad 400 volt capacitors, if you arrange them like this, then it's effectively an 800 volt 50 microfarad capacitor. But in order to keep the charge on these two similar and prevent the charge building up on one more than the other, you generally speaking have to put a resistor across each one. So you'd arrange a couple of resistors like this. Now the bottom one you might want to use for something else, but for now we'll just connect it in this mode. Now a lot of people seem to assume these are here to discharge the capacitors when you turn the supply off, and they will indeed be useful for doing that, but they're really there to balance the charge across the two capacitors and make sure they share the workload equally. Now the value for these is normally in relation to the capacitor capacitance itself, so it will be something, the recommended rule of thumb is 50 divided by C. Now I actually normally use something nearer the 40 divided by C value. It seems to work better for the applications I've designed, but you can use either one, it's not critical. Just don't go too low, otherwise you'll be dissipating a lot of energy and also creating ripple in your supply. Now the ripple here is not that critical because this is not the output of our supply, of course, and this will be chopped quite severely anyway. And if we want to now make this multi voltage, then all we have to do is take this point, bring it down here, we can put a jumper or a switch in, and then we can take that to here. So when this switch is closed we have 110 volt operation, and when it's open we have 220 volt operation. So the way this works is easy to explain if I draw in the diodes that would be in the bridge rectifier. So they would be arranged like this. So if we have positive here and negative here, the positive comes down through the switch, if this is closed, to the positive side of this capacitor, and then negative comes down through here to the negative side. When the phase is reversed, so we now have positive at the bottom, we've got negative up here, that comes through here to the negative side of this capacitor, positive then comes through here to the positive side of this capacitor. So it's acting as a voltage doubler when we're in 110 volt mode. With a switch open, it just acts as a bridge rectifier, full wave bridge rectifier, and these two capacitors are used as if they were a single capacitor. So that's how it's arranged. I'm most likely, as I say, going to use a single capacitor here, but it's up to you whether you want to make the slightly extra complicated design and allow your unit to operate at two completely different voltage ranges. Now the advantage of doing it like this is it means that what follows on from here can be identical for either 110 volts or 220, because the voltage here will be the same. So this voltage is going to be the same whether you have 110 volts on the input or 220 once you've got the switch in the correct position. And as far as what the voltage is, as I say, the voltage, the main supply where I am is about 250 volts. So the voltage here is going to be somewhere around, once it's rectified and smooth, is going to be somewhere around 350 volts. So this is what I was saying about it being potentially quite dangerous. So having fairly large capacitors, so these probably be 100 microfarad capacitors, having that amount of capacitance with this voltage can be lethal, so just be very careful when you're playing with this. And in fact, to start with, I'm not going to use it on the mains. So although we've just designed this, we're not going to use this initially for the demonstration and testing. You can also, of course, run this on DC. As I've shown in repair videos, you can just feed relatively high voltage DC into this. So 60-70 volts is normally enough, and that will actually run this. It doesn't need to be AC. It will work fine on DC. But again, just bear in mind that can be quite dangerous, but by using a bench supply you can current limit it, and it does make it somewhat safer. Also, the bench supply is fully isolated as well. So now we've got this part of the design sorted out, we have to decide how our switching supply is actually going to work. So the next thing we have to do is design the actual switching part of the supply. So we have our V plus coming in here. Remember, that's 350 volts, and that's our input supply rail. And then of course we have 0 volts. And that's the 0 volts on the input supply as well. It's not the 0 volts on our power supply output, it's just the input. You could tie them together, but it's not normally a good idea doing that. You want fairly good isolation between the input and output, so it's best to leave this completely separate. Remember, this is part of the main supply, so you need to be very careful what you connect to this. If you connect this to the outputs, one of the outputs of your supply, then you're effectively mains referencing your entire supply, so it's not a good idea to do that. Okay, so what we're going to have, of course, in a switch mode power supply is a transformer. So we'll start and we'll have the primary of the transformer. We're going to be driving the primary, of course, and we'll have, in our case, multiple secondaries. I'll go over what secondaries we want in a future video. But just bear in mind that what we're looking at in this video is just how to get the general switch mode supply up and running. So we'll start with the primary of the transformer, and we need some way to switch current through it. So we're going to use a power transistor. Now you could use a MOSFET. The reason I'm not doing that is because I want to try and keep the general feel of our Z80 project the same. I don't want to start sort of dipping into more modern devices. Now MOSFETs have been around for a long time, of course, so they were available in the period we're talking about, but more typically this type of supply used a bipolar transistor, so that's what we're going to use here. So this will be a fairly high voltage transistor. It will need to be on a heatsink, but I'll come back to the type that I'll use later. I repair a lot of switch mode supply, so I've got quite a lot to choose from. NPN, of course, but the next thing to do is decide how we're going to drive it. We could build an oscillator and use that to have pulse width control. I would also point out here, this is not the same as a switching regulator, where we have a pass transistor that's being switched in and out through a capacitor and inductor. This is a true switch mode supply, so we have proper isolation. The advantage here is if this transistor goes dead short, for example, we don't feed high voltage through to the output. The system just stops and the output drops to 0. Whereas when we have a pass transistor feeding a switching regulator, if that pass transistor goes short, it will feed a relatively high voltage directly onto your 5-volt rail, for example. We don't have that risk here. We do, however, have the risk that if this transistor turns on and stays on, we're effectively putting 350 volts DC directly through the transistor, and it will of course blow it to pieces, so you do need to be fairly careful with this. Now in general you wouldn't build a separate oscillator. You can do, but that's not the way you'd normally go about arranging for this type of circuit. So if we look at the way these are normally arranged, and we'll take the current at this point in the circuit. So imagine if we switch this transistor on, the current in the node here is going to start doing something like this, and then if you turn it off, it's going to start doing something like this. So because we're driving an inductive load, we have kind of a grace period, if you like, when we first turn the transistor on, that we're not going to get a massive current flowing through the inductor. It's going to take a finite time for the current to ramp up. Now when it's doing that, the current's going to be increasing. So what we can do is we can actually put a resistor in the emitter part of the circuit, and so the voltage at this point is going to do something fairly similar. It's going to ramp up when the transistor turns on, and it's going to ramp down when the transistor turns off. So we can use that to actually control the transistor. So all we have to do is we need to feed the transistor with some base bias currents. We need some current going into the base, and we can arrange for that by simply taking a resistor up to our positive rail. I mentioned earlier that you can use this bottom resistor in this network for other purposes. So what you can do is disconnect it from here and then use this point as this point. So you can, if you want to, make this resistor function as this base bias resistor for your driver transistor. To keep it simple, at the moment we'll assume we're not doing that, so we'll just build the test circuit like this. Now in this arrangement, what would happen is, of course, the transistor would just turn on and it would blow itself to pieces because it would stay on. So we need this to turn off once the current reaches a certain level. You can calculate the values needed for these. This will be a fairly low value resistor, usually much less than 1 ohm, because we're getting quite high current spikes. And what we need is a voltage here that we can use to control another transistor. So we'll take a voltage here and we'll use that to switch another transistor, and again it will be another NPN transistor, and we can arrange it like this. Excuse the poor drawing. So what we'll get here now is it probably wouldn't run like this, but in essence the way this is going to operate is when we first apply power, we'll get current flowing down through this resistor. It will feed current to the base of this transistor. This transistor will turn on. The current will start to increase. The voltage here will start to increase. That will turn, at some point will turn this transistor on. That will pull the base low, and it will start turning this transistor off. And then the cycle will repeat. So that's the basis for our oscillator. Now we do need to make some changes to this so that it will operate cleanly and effectively. So the first thing we want to do is make sure that when the transistor turns off, that we don't destroy it with the resulting back EMF pulse from the inductor. Remember, this is a large inductor. So we need some kind of network on here to act as a damper for those spikes. It will also make the system more efficient. It will prevent us destroying the transistor. It will keep the transformer from overheating quite so quickly. So what we can do is put a diode in here and feed that through a resistor back to the positive rail. So when we get the back EMF spike, it's actually damped out back to the positive rail, and then we can further filter this with a capacitor. And I'll show you the effect of this in a few minutes. We'll build a test circuit and I'll demonstrate this. Now that is fundamentally the basis of the switch mode supply, and if you've seen old switch mode supplies, this should look familiar. Normally there's a lot more complication down here, and we will be adding that later on, and that's part of the regulation circuit. In fact, most of the complexity here is the regulation feedback circuit. We'll have a closed loop. But for now what I'll do is just add a resistor here that's not connected to anything, and we'll come back to what this is for in a few minutes, and I'll demonstrate the general way this circuit is going to operate and behave. So what I'll do now is I'll build this onto a breadboard. We're not going to go for the high voltage version or even a real transformer. I'm just going to build a demonstration circuit using some small signal transistors and I'll show you how this circuit will operate, and hopefully will help to explain the design as we go through developing the actual switch mode supply. So I'll get this built up and we'll go from there. So I've built this exact circuit onto the breadboard here. I'm just using a couple of BC547s, so these are small signal transistors, and I'm just doing this to demonstrate the way this circuit works and how we're going to develop our proper switch mode supply. But I just want to demonstrate this circuit first, just to clarify what we're aiming for. So I've got this hooked up to the bench supply. Bench supply is set to 9 volts. It's not hooked up to the bottom one you can see, it's hooked up to the one above that. This one's actually driving the lights that we're using for illumination. The main lab lights are being used for something else. So I've got this set to 9 volts. Current limit's up at about 4 amps, so if this turns on and doesn't turn off, it will destroy the transistor. We could current limit the supply, of course, but I'm trying to demonstrate here the need for this circuit to operate properly. So we'll turn this on. The scope is connected to this point. It's connected to the collector of our driver transistor, and the transformer is just a ferrite core with about 15 turns of wire on it. It's not critical at this point, it's just to give us an inductive load that we can use to demonstrate the circuit. So we'll turn this on, and as you can see, it's oscillating, and not only that, it's quite nice. It's giving us a good strong switching effect. It's not unstable. It's drawing about 40 milliamps, so it's actually running quite nice and efficiently. Now what you'll notice with this, because there's no load on this, it's just kind of floating in space as far as it's concerned. So from a hand near it, you'll see it changes. You see on the scope the signal's changing a lot. Now it will stop doing that once we put a load on it. It's just at the moment it's very susceptible to anything that moves around it. But as I say, that's just because we're not loading it up. It's just kind of floating, and there's nothing to damp that down. So now we know it's oscillating. Incidentally, it's running at about 300 kilohertz because we've got a small inductor, and of course that's going to affect the frequency of oscillation. What we can do now is turn this into an actual transformer. So what I'm going to do is put another, I'll just switch it off, I'm going to put a single turn through the transformer, and we'll hook it up to something so that we can see that it is acting as a switch mode supply. So I'll just hook up an LED, and we'll see if we can get that to illuminate. So I'll put a single turn through the transformer. I've just hooked it up directly to an LED. No resistor, it's just hooked directly to it. And I've got the second channel of the scope hooked up to the output of our winding, our secondary winding. So we'll turn channel 2 on, and we can now power it up, and we should see a signal on the output of the transformer, and also the LED should illuminate. And as you can see, that's actually working fine. So we now have what amounts to a switch mode power supply, and it's as simple as that. That's all we need to do. Now it gets more complicated from here, of course, because we actually have to start getting into the design. But the next real question comes down to the feedback loop and regulation. So you'll remember I added this resistor, and that's this resistor here. It's a 100k resistor, and what it's going to be used for is part of our feedback control loop. So I'll connect a lead. This is just a test lead, and the other end of this lead, what I'm going to do is connect it to either 0 volts at the power supply or V plus at the power supply. So it's connected to 0 volts at the moment, and you notice that the LED has gone off, and the purple trace, which is the output of our transformer, is quite low. What I'm going to do is just turn up the supply voltage until the LED just starts to come on. So as you can see there, the LED is just starting to come on. It's about 10 volts now. Don't know if you can see this, the LED is glowing, but it's quite dim. and you can see the purple trace is relatively low. I'm going to now move the input to this point, so again that's here, so I'm going to move that. It's currently at 0 volts. I'm going to move that now to the positive supply. If you notice, the LED gets much brighter and our signal goes up. So I'll move it back to 0 volts, keep an eye on the LED or the scope, and once again the output voltage drops, and we'll go back to V+, and it goes high again. So in other words, even though we're feeding this in through a 100k resistor, we've got a lot of control over the output of our system. Also notice that it's now far less susceptible to external influence than it was before. As I said, once we get this properly loaded up and laid out, that kind of goes away. So at the moment we're using quite small signals here. But the issue here, or the point here, is that we can use this point in our circuit as the input, the regulation input. So we can use that to modify the amount of energy we're passing through the transformer. So in fact the way this will work is we'll have feedback from our output, isolated output side, and that will feed back and it will control the voltage at this point, and that will be used as our closed loop feedback system. So all we have to do is arrange to have the voltage here vary in relation to the output voltage, so that we can regulate what the switch mode supply is actually doing. So it's quite straightforward. It gets a bit more complex to actually make this work properly and also have the step response and startup response as we want it. But hopefully you'll get the idea that this is, or you get the idea how the circuit's actually going to function. And you can see on a small scale here, it's quite easy to organise. Bear in mind that at the moment we're drawing about 44 milliamps from the supply, even though if we were to just switch this transistor on and not switch it off again, that's this one, at the moment the only thing limiting the current is a 0.2 ohm resistor and this winding on the core. So it would draw well in excess of an amp even with an arrangement like this, and that would destroy the transistor. So you can see here that although we have the potential for this to fail catastrophically, it's not. It's working fine because the circuit is doing what it's supposed to. The last thing I want to demonstrate before we move on is this part of the circuit here. That's these components, and I said these need to be here, otherwise we'll get all sorts of noise and issues on the switching. So what I'm going to do is just remove the diodes. That's this diode here. I'm just going to take it out, and then hopefully you'll see what effect that has on the switching of the circuit, and it's probably going to be more dramatic than you might expect it to be. So I'll just take this out. I'll switch it off first so I don't blow anything up while I'm taking this out. Okay, and what I'll do now is turn the power back on. If you look at the scope, you'll see that the switching is very poor. It's not switching cleanly like it was before, and also the voltage spikes are very much higher. So we'll just reduce again on that channel. It's now at 20 volts per division. You can see how high this is going, so we're getting nearly 80 volt spikes on this, even though we're only feeding this from a 10 volt supply. So I'll put the diode back in. I'll just switch this on and off a few times so you can see that it's consistent. It's the same every time. And I'll put the diode back in and you'll see what effect that has in terms of damping down that high voltage spike. So turn it back on. So you can see now that it has a very good effect, and we can tailor that to limit it to whatever we want by selecting appropriate values for the resistor and the capacitor to filter this as we want. And it also allows us to control the switching of the main transistor. We will also need a filter across this in our final version to control and optimize the switching characteristics, but before we can do that we need to get the transformer sorted out so we can calculate the value that we need for this. So what we'll do before we finish this video is just have a quick look at the type of transformer that we'll be using for this, and try to calculate the number of turns, or at least the initial number of turns that we'll require on the primary, this winding here. So I'll get this out of the way and we'll just have a quick look at that. So we've taken a brief look at the circuit type that we'll be using, and the next thing is to determine the type of transformer that we'll be using. Now, with switch mode supplies, the transformer selection there's a whole range that you can select from, different types of core, different core material, different formats for the way the transformer is laid out. But there are some fairly standardized ranges now. It's a lot easier than it used to be, and all we really need to do is determine the size of the transformer core we need. And I tend to err on the one size higher than I need. If you're trying to optimize it, you might want to go smaller. But we need 3 rails for our system. We need an 18 volt rail at 1 amp, we need a 5 volt rail at 3 amps, and we need a 12 volt rail at about 0.3 amps. So we're talking about 35-40 watts. So I'll be using a core that's suitable for about 50 watts, and that will give us a good scope. We need to make sure we don't saturate the core. We need to make sure that we do make reasonable use of the core, but we need to generally err on the safe side, which is to underdrive the core. If we overdrive it and the core saturates, it will start to overheat. If we go too far, we'll destroy the driver transistor. Now, there are multiple calculations we'll need to carry out. Like I said, I'll try and steer clear of most of the maths for the sake of the videos, otherwise they will get a bit long-winded and boring. But the first one we need to look at is to calculate how many turns we need on the primary of our transformer. We know we're going to use a 50 watt type switch mode supply transformer. The specific calculation will depend on the one that I select, but as a general rule of thumb, a good formula to use is the number of turns on the primary is equal to the voltage, the nominal maximum voltage that we'll apply. So that, if you recall, that was 350 volts in our case, and you multiply that by 10 to the 8th. So it's quite a big number, but it makes the calculation fairly easy to use as getting a ballpark figure for the number of turns on the primary. There are quite a few things that affect this. You may have noticed that as we loaded up the circuit, and as the regulation voltage was varied, the frequency changed, and that's something you need to be aware of, that although this is a good rule of thumb formula that we'll be looking at here, there will be other things that will influence it, and then the maths does tend to get fairly complex, but I'll try and keep it simple, and you can probably use this as a starting point if you're willing to experiment with the design. So we start with our supply voltage times 10 to the 8. We then divide that by 4 times the frequency, and that's the switching frequency for our system. I'm going to start with a nominal frequency of 100 kilohertz here, although the circuit we were just looking at was operating at around 300. The circuit we design will be operating quite a lot lower. It's going to be much more inductive, although we will be driving it much harder, of course. And then we multiply that by this is the flux density of the core while we're driving it. That's a maximum flux density we want to drive it to. So that's what's called Bmax. And again, that will depend on the core type. And we multiply that by the area, cross-sectional area of the core. So we can plug values into this. So the Vmax we know already is 350, so it's 350 times 10 to the 8. And then we divide that by 4 times, and we want 100,000, that's our frequency of switching. Maximum flux density we're going to use in the core type that we're going to be using is going to be about 1,500. and then the cross-sectional area is in centimetres squared. And for the core type we'll be using, that's going to be somewhere around the 1.7, 1.75 range. So I'll just work this out, and that will give us the number of turns for our primary. So I'll get the calculator and we'll see what this comes to. So if we work this out, it comes to 343. So that will be the nominal number of turns we'll need on our primary for the type of transformer that we're going to be using. Now this will probably need to be changed. I'll need to include some other parameters to our calculation, because it will be modified, as I said, when we start introducing the feedback regulation. But this is a good starting point, and it gives you an idea as to the number of turns we're going to be needing. So it's not going to be vastly different from this, but we do need to take into account that we'll be regulating this supply, so we won't always be driving it in the exact same level. It depends on the output loading. For example, if there's no load on the output of the power supply, then it will be very different to if it's heavily loaded. In fact, you'll find some of the supplies of this type, if you don't put a load on the output, they won't start up. You'll hear them ticking, but they won't actually run properly, and that's for this reason, that they will only operate over a fairly limited window of loads and voltages. So that's the reason that they do that. It's not intentional, it's just that if it's operated outside of the acceptable regulation window, then it probably won't run at all. So as I say, this will be the starting point, and in the next video in this series we'll start putting together the actual circuit we're going to use. We'll start looking at a transformer. We'll probably wind a primary onto the transformer, and we can start then calculating the windings we need for the secondary, and we can then start looking at the feedback control loop and how to optimize that to give us the response and regulation that we actually need.